Hello everyone, welcome to the first lecture of Operating Systems Engineering course. I am Arvind Mechri. I'll be the instructor for this course this semester. About this course, so this is an undergraduate level operating system course. In this course, we'll be understanding basic operating system concepts and mechanisms. We'll be doing them with uh, labs. Uh, there are 5 labs. We also have midterm and final in this course. And in order to understand this course, it's really important that you have taken data structure course, and also you have proficiency in C. By this, I mean, you know how to write programs in C that use a lot of pointers and recursions. You know how to manipulate bits in C, and basic pointer manipulation and pointer arithmetic, and how to address memory using pointers, so on and so forth. A brief introduction about me. I'm Arvind Mechri. I finished my PhD last year from University of California, Santa Barbara. Before that, I did my master's at Georgia Tech. My research interests are primarily system security, where I work on security of operating systems and IoT devices. I'm also interested in program analysis. Specifically, I use static and dynamic analysis techniques to analyze programs. I'm also part of Purdue Systems and Software Security Lab, which we call like PERS Lab. So in PERS Lab, we focus on modern system security, where we pursue various research directions like vulnerability detection and security and machine learning. Basically, we try to use machine learning techniques for various system security problems. We also try to retrofit security to existing systems. We also work on securing operating systems, binary analysis. Actually, we are working on a system that can automatically apply security patches to the binaries. We welcome undergraduate research. So if you are interested in doing research in system security, please email me. So let's look at a typical computer from hardware point of view. From the hardware point of view, a computer contains CPU. CPU stands for like processor, central processing unit. It has memory, and we have chipset that controls, that basically is an integrated circuit that connects all the components. We also have various input output devices like disks, printer, monitors, and we have network cards, we have mouse, so on and so forth. This is from hardware point of view. However, when we look at how we use the computer through various programs, like users use program compilers, assemblers, text editors, or various games, and this is how we use the computer. And we need to have the component which actually translates the use of computers into the hardware. Like whatever uses that we want to make, those need to be translated to the computer hardware. For instance, at the hardware level, we have disks. So disks, magnetic disks are used to store data. So when you look at hardware level, so magnetic disk contains blocks, and these blocks are addressed using physical sector numbers, and these have various properties like if the machine crashes, the data gets corrupted, and in order to store data into these magnetic tapes, we need to load values into specific device registers. For instance, if I have to store some, for instance, my lab one solution, the way I can store is I need to say the platter number, track number, and also sector number. This is very tedious. So in order to facilitate the communication between programs and the hardware, that is where operating system comes into picture. So the main goal of operating system is to make sure that it provides a uniform interface for the application programs so that they can make efficient use of hardware. So instead of using hardware directly, what operating system provides is it provides a nice abstraction called file systems. So where we don't need to worry about blocks and sectors, which are very specific to hardware. Instead, we save, we store files by using directories and file names. And this is very uh, easy, and it's easily like it can be done easily by programs. And this is uniform in this independent of the hardware. The hardware might change, whereas the file system abstraction will remain same across different hardwares. This is very convenient. S- So, a brief history of before understanding what operating systems are, let's look at how operating system evolved. So, at the beginning, the first set of operating systems were simple batch processing systems. So these back in batch processing systems, the computers, like the operating system, usually had one job to do. So users submit a job once, and operating system just does the job until the job finishes. So there is no interaction, and all the things that are needed by the job have to be specified before the job gets executed. So, and the computer does all the work without any manual intervention. And it also, it's very performant, right? Because you just specify all the things that are needed by the job, computer runs the job uninterrupted. However, it's very hard to debug programs written this way, because any job that starts, we cannot debug it until the job finishes. Imagine if the job has an infinite loop, then the computer just never terminates. And also, because of the lack of protection schemes, we can have one job affecting other job when they run one after the another. Because if the resources are not cleaned up, then we can have one job writing to a file system, and and can fill up the disk, and the other job may not have any space on the disk. The second generation of computers are multi-programming systems. So here, the goal of these multi-programming systems was efficiency. Previously, we had batch processing systems where there was only one job running at a time, whereas in case of multi-programming systems, we have multiple jobs loaded into memory, and these jobs are scheduled onto the CPU by the operating system. So the main goal of operating system here is to schedule CPU. It needs to make sure that there is always CPU is always running certain job. So it needs to switch the CPU for various jobs that are in the memory. And the advantages of this system are efficient utilization of CPU, because now the CPU can switch between multiple jobs. So if a job is stuck, or it's waiting on input output, or it's waiting on disk writes, it can be switched to another job which might have something to run on the CPU. The disadvantages of this systems are CPU scheduling. Right now, operating system needs to be smarter in order to schedule CPUs to different jobs, and it also needs to make sure that the scheduling during scheduling the jobs are not corrupted. And also, in order to manage various jobs, it needs to manage memory, which is also a limited resource. And the third generation of systems, uh, these are called time sharing systems. These are similar to multi programming systems. However, the switching happens so quickly that users can actually interact with the programs. So here, each program is given a fixed time slice, and very small fixed time slice. So, and multiple programs will be switched after that particular time slice is finished. So it's more complex than multi-programming, because there is this continuous switching, and also, because of the continuous switching, now the operating system needs to be more efficient, because in order to switch, it needs to perform various tasks. Furthermore, there are this fast switching also gives rise to various problems like concurrency, and communication between different processes becomes complex. And there are various other issues that occur in time sharing systems that we'll be looking in this course. And most systems today are actually time sharing systems. And this will be the focus of this course. So now, given knowing the brief history of operating systems, let's uh, let's ask ourselves, what is an operating system? So as I mentioned before, so operating system is the code that sits between programs and hardware. It's also the code that sits between different programs and different users. And how does operating system achieve? How does operating system achieve all the goals? How does it sits between programs and hardware, and how does it facilitate the efficient use of hardware to, by the programs? So the way it does is it mainly provides two important things. The first one is it acts as a resource manager, and the second thing is it provides a nice abstraction. You can call it as an abstract machine. Basically, it removes all the nitty gritty details of the hardware and it provides a uniform interface for the programs to use the hardware. So, as a resource manager, operating system does three things. One, it allocates the resources, it reclaims the resources, and it also protects the resources by from contention, and also makes sure that the programs don't use each other resources. So, first, in order to allocate, it needs to allocate resources. Mm, Examples of resources are in CPU, memory, disk, and network card. So, since these resources are fixed, it needs to make sure that the resources are allocated to uh, each process for efficient use of these resources. And also, once the resources are allocated, it also needs to make sure that the resources are reclaimed, or else a process might just hog the resources and it can make them unavailable for the other processes. So it needs to make sure that these resources are reclaimed. Either, I mean, the reclamation is kind of implied at termination, because when the process terminates, all the resources are reclaimed. Also, few resources are actually uh, preemptively taken from the process when they are needed by other high priority processes. And reclamation can also be cooperative. For instance, a process, when it knows that it doesn't need CPU anymore, it can actually yield CPU so that operating system can use the CPU to run other processes. Finally, it also needs to protect the resources so that the resources are not overused by the processes. And it needs to make sure that the resources are not abused by um, malicious processes or improperly working processes. And the other thing that OS provides is it provides an abstract machine. Basically, what I mean by this is operating system provides an abstraction which is independent of the hardware. So here, irrespective of the disk that we use, it can be either magnetic disk or SSD, we always have a nice file system interface, right? So the interface is fixed irrespective of the hardware we used. And the operating system provide this kind of abstraction for all the other hardware resources. So, and this makes it much more ideal environment than actually dealing with the hardware, because we can write programs without worrying about underlying hardware, because we can use the abstraction provided by the operating system to do this. And this abstraction provides a nice way to look at hardware resources without worrying about exactly the number of hardware resources. For instance, irrespective of the RAM memory, like RAM we have, we can always think of RAM as a single sequence of bytes. And that's exactly the abstraction provided by the operating system. And the way operating systems achieves this is there is a fundamental design principle in computer science where which says to separate mechanisms from policies. So we can think of mechanism as the hardware and policy as a task that needs to be done by the process, or like that needs to be done by the user. So mechanism is how the task is done, but policy is what task needs to be done. So operating system kind of separates these two things, and thereby it provides a nice abstraction. There is other design principle called indirection that's also commonly used in operating systems, which we'll be looking into more details as we look at other aspects of operating systems later in this course. Let's ask ourselves, is there any perfect OS? Unfortunately, no, because the operating system design is a complex thing and the requirements change because operating system have to balance between various conflicting requirements. For instance, it needs to make sure that the resources are used efficiently and also needs to ensure that the resources are used fairly among various competing processes. And it also needs to make sure that the uh, processes don't attack each other or there is enough security between different processes. At the same time, it also needs to make sure that there is efficient communication mechanism between different processes. So these are actually conflicting requirements, and operating system needs to balance between these conflicting requirements. And there are also other things that make design of operating system very complex task. Hardware is evolving, right? So we had mainframe computers in 70s and we evolved to mini computers and PCs came, and now we have mobile systems, internet of things, and we have these small computers at every step of our life. And consequently the design goals of operating system changes because the hardware changes, and the things that we expect from machines changed. Previously, and the mainframe computers, the cost of these machines was also huge. Like these are very big machines, and they were very expensive machines. And now, as the cost decreased, we have like these machines have become very cheap. You actually can get a computer for like $10. Raspberry Pis are available for $20, which are fully working computers. The the cost of the systems, the hardware has decreased. Furthermore, the performance goal of operating systems also changed because the utility of these microcomputers that we use has also changed. Previously, it was all ensuring that the machine is efficiently used, but now the goal is to ensure that the user is more productive. It is to ensure that the user is actually efficient in performing his or her task. And and also there are new architectures coming. Like we had x86, now we are using ARM, and we are also using OpenRISC. There are new architectures coming every now and then. Furthermore, there are new memory technologies that are coming, new storage techniques, new network devices. We are now into gigabit network cards. And also there are new processors. We have graphics processors. We also have specialized processors that are designed to perform one particular task. For instance, there are actually neural processors that are designed to be efficient to perform machine learning tasks. And we also live in interesting times when it comes to physical improvements to the hardware. Like processor speed has doubled in 18 months, and number of cores is also doubling in every 2 years, and disk capacity is doubles every year, and the bandwidth is also doubling every year, every 6 months actually. So and the performance and cost sweet spot is constantly moving, and the assumptions that we have on the hardware and the design goals that we had before are no more the case. Like they are changing in within months time frame. So it's really hard to design operating system that can keep up with with all this evolving hardware. And also, applications are also evolving. Like previously, we had batch processing applications where most of the tasks were just mathematical computation. But now, the applications are wholly different set of applications. Now we are looking at interactivity. We are looking at mobile applications which are designed to do one specific task. For instance, previously we had programs that could do many tasks. However, now we have these apps which are very designed specifically to perform one task, but in a very interactive and efficient way. And we have virtual reality applications, and the demand for these applications is different from the operating system than the traditional applications. So, and what it does to the operating system is the design of the operating system needs also to be evolving along with the evolving hardware and evolving applications. And unfortunately, there is no magic bullet to the good OS design, because the requirements or the demands of the operating systems are constantly changing. Furthermore, most of the operating system design is engineering. So, as we all know, engineering is imperfect. Most of the engineering decisions are trade offs. And and since we don't have and since the requirements are changing, and the hardware needs the operating system design is also cannot be static. It also needs to be evolving over time, and nothing is permanent uh, when it comes to operating system design, because the things that we assume today may not hold in 6 months down the lane. If we are optimizing our operating system for efficiency or for storing or for good compression, but that requirement may be different in 6 months when the disk rate goes down and we no more need compression. Maybe we could trade off compression, we could use the time to do something else. So the requirements keep on changing, and it's very challenging to have a, a OS which is good for all the purposes that we need. However, there are few things that we know operating system has to take care of, irrespective of the changing hardware and changing requirements. Operating system uh, still needs to take care of concurrency. It still needs to handle different processes. It still needs to manage hardware resources. So there are few things that are static, that are always fixed. So in this course, we would be learning the basic principles of operating system design. We would be learning the fundamental things that any operating system that we design should take care of. And we'll do this with a lot of practice. We will have projects that we use to test our understanding on various operating system design principles. And we also have midterm and final, where we test our concepts at much more theoretical level. And in this course, we'll be looking at various design principles in operating system, which are fixed irrespective of the other things uh, that that keeps on evolving in operating system. There are few things that are fixed in operating system that it has to take care, like concurrency, protection, security, performance, reliability. So these are the things that operating system needs to take care. And so in this course specifically, we'll be covering process management and memory management, input output management. We'll also be looking at protection and security. And if we have time, we'll also be looking at more advanced topics like virtualization and containers. So this course is not will not be easy. So you can expect a lot of programming projects. So there will be a few labs would be specifically uh, like they would be hard, and you may spend time you may spend actually a lot of time debugging your code and staring at some code and trying to get your head through some difficult concepts. But we'll learn these things together. We'll have nice examples, nice videos. We'll have Piazza form to discuss. So don't worry. we'll get through this. A few mechanics for the course. So as I mentioned, I'll be the instructor for this course, and that's my email, and the office hours will be on Thursday. And I'll be posting, I'll be conducting my office hours over Zoom, and I'll be posting the link on the course webpage. And you can also have office hours by appointment. And TS for this course are Hajin, Sushant, Gokulan, and we have Sahil. And TA office hours and location. Mostly it will be online TA hours, and the details for this will again they're yet to be decided. So I'll be posting them on the course webpage. So the course webpage is as shown on the slide. So all the announcements will be made on Piazza and Brightspace, and specifically most of the discussions will be on Brightspace, on Piazza, and the grading will have grades will be given on Brightspace. So for question and answers, we'll use Piazza for for our question and answers, just because it's easy uh, to ask, and questions can help other students to understand concepts as well. And for other questions related to grading and project related questions, you can ask TAs. And all the official announcements will be made on Brightspace, along with the email notice sent to all the students who are enrolled. And textbook for the course, there are two textbooks. You can use either of them. The first textbook, which I prefer, is called Dinosaur Book. It's Operating System Concepts by Galvin and Gang. So you can either, I'll be using 8th edition of this book, so you can use 6th or 7th edition. Most of the content stayed the same. And this book is very good because it explains concepts really well, along with nice illustrative examples. And there's also another book, we call this Comet book. So this is a free online book. It's called Operating Systems, Three Easy Pieces by Remy and Andrea. And this explains in a much more succinct way. And it's very nice to use this book as a refresher. However, when you're reading for the first time, it's better to use Dinosaur Book. So there may be few lecture notes. However, most of the content that I'll be presenting in this course will be from the textbook. However, if there are some lecture notes, I'll be posting them on the course webpage. And uh, and please try to ask questions, because this course is a hybrid course. Uh, I'd be recording all the lectures. Uh, However, if you have any clarifications or any doubts regarding the course, please do not hesitate to ask questions on Piazza, or you can email either me or one of the TAs with your questions or concerns. So regarding projects for this course, there will be 5 projects or labs. All the labs are done remotely, because I think the labs are closed now. I'm not sure. I still need to check for this, but I think labs are closed. So, however, all the labs can be done remotely, so we don't need to worry about that. So here in the labs, we'll be mainly building parts of the operating system. So we'll start slow with like basic processes, system calls, and then we'll eventually end up with actually building our own file system. So first lab is not graded. It's just for you to set up the DLX operating system and go through the tutorials. Just basically set up your environment uh, all the for the rest of the labs. And each lab will be 3 weeks, and we'll be explaining what each lab, what we do in each lab, and each lab will be due after 3 weeks, and the exact date, you can refer syllabus for the exact date. And except for the first lab, all the other labs are expected to be done in pairs. So please find a partner for the lab, and send the name of your lab partner to the TA once you decide on the lab partner. So the reason why we do labs in pairs is because pair programming is actually good. It's actually shown that doing coding in pairs actually improves the cumulative understanding of both the both the students who are part of the pair. So it's really important that especially to understand certain concepts, it's really helpful if the projects or labs are done in pairs. So since since labs are done remotely, so the collaboration would be, I think it's mostly remote. So please start labs early. So don't wait till the last moment to start your labs. So when the lab is out, make sure that you start lab right away. And coding pair programming can be done through screen sharing. You can schedule Zoom calls with your partner and share the screen and try to do pair programming remotely. And you can have debug sessions also remotely. And if you start early, you can actually use lab sessions to actually ask questions to the TAs. So more lab sessions, I think they'll also be remote. So you can actually schedule calls with the TAs so that you can ask any clarification questions regarding lab sessions. So it's really important that you start the labs early because they are remote and it'll be challenging to get them done in time if you don't start early. And as I mentioned before, there'll be midterm. It'll be just before spring break, mostly in the evening. However, you'll be given 22 hours. You can take midterm anytime within the 22 hours period. And the final will also be in the similar format. However, finals will not be cumulative. Basically, we'll cover half of the content in the midterm and the other half in the final. And these exams are mostly multiple choice questions, true or false answers, true or false questions, and there'll be short answers. There'll be some design questions, but not much verbose questions. Most of them will be very objective, and there'll be no ambiguity in the answers. So regarding grading, uh, projects or labs will have 55%. We have midterm and final 20% each, and there'll be 5% for the participation. The participation can be either online participation on Piazza, or it could be in the class. In the class, you can ask questions in the class, and there is no late policy. So because you have enough time for the lab sessions, unless there are some health reasons, there will be no extension for the labs. And academic integrity. And so if whenever in doubt, please ask TS for the clarification. And each team is expected to write their own solution, and we don't we don't expect teams to share code. However, if you happen to use code from any online sources, please explicitly acknowledge them. And furthermore, it's your responsibility to make sure that your labs that you do are safely secured on the machines that you use to do the labs. So make sure that when you do the lab, you save the file somewhere, or and like all the permissions on your folders are set correctly so that nobody can delete the files, so on and so forth. So it's your responsibility to make sure that the project's files are there on the machine so that when you log in again, uh, the files are not deleted. Okay. And regarding academic integrity, the first case of cheating, will run automated code checkers to make sure that students or teams did not cheat on their lab assignments. However, uh, in unfortunate situation, the cases of cheating is caught, and they will be reported to university administration accordingly. However, if multiple cheating attempts are caught, you'll be given an immediate F grade for the course. So regarding ABET outcomes, so by early March, we'll have the document explaining mapping labs and course content to various ABET outcomes. And we'll also have remediation homework again by early March. And that's it for today's lecture. So for the next lecture, which is on Thursday, I expect uh, you to read chapters 1 and 2 from the dinosaur book, or you can also read chapters 1 and 2 from the comic book. And please, the lab 1 is out, so please start lab 1 now. uh, and go through the instructions. Lab 1 might be tricky, so however lab 1 is not graded, so make sure that although and also please find your partner and email the TAs corresponding to your lab as soon as possible. Make sure that you find your lab partner before February 2nd. That's 2 weeks from now, because that's when lab 2 starts and you are required to do lab 2 onwards in pairs. That will be all for this lecture. Thank you.